Hello everyone, and welcome back to the Tech Recruiting class. In this video, we're going to look at some exercises regarding trees and graphs. So if you haven't already checked out the video where we introduced some concepts of trees and graphs, we'd encourage you to do that now. The first question we're going to look at revolves around a binary search tree. For this binary search tree, we're going to check a property. And this property is that it is height balanced. And so if you see this question in an interview, the first thing you would probably want to do is, reread the question, make sure you understood it correctly, and then ask, what does it mean to be height balanced? And this is a good question for your interviewer because this isn't a definition that you should know offhand, and definitions may vary from the one you know and the one your interviewer knows. So for a binary search tree, we are going to say the binary search tree is height balanced if any path from a root node to a leaf differs by at most one. And this is made a little bit more concrete in examples. So for example, here, that's one path from a root to a leaf. It has height 2. This is another path from a root to a leaf. It has height 1. The absolute value of 2 minus 1 is 1. And we're going to use absolute values here because we only really care about the relative distances. Let's say we had this situation. Well, then one path from the root to a leaf has height 3, and one path has height 1. 3 minus 1 equals 2, which is greater than 1, so it's not height balanced. And so with the definition of height balanced, we're ready to start the problem. The first way we could attack this problem is in a very brute force kind of sense. So let's say we wrote some method called depth. And for this method, we could check the depth of every leaf. We could recursively call depth on all subchildren until we reach a leaf, at which point we could determine the pair of that leaf and its depth. We could then store this in some global data structure and then run through and compare all depth values. However, we're going to have to compare all these depth values to each other, but this doesn't seem like the best approach. It seems like a lot of steps and a lot of runtime. So let's see if we can think back to our original example. This was a height balanced tree. We might be able to look at the subtrees, right? So let's look at this left subtree. It's a balanced tree, assuming this is our root node. Its subtree is also balanced. Similarly over here, we know this is just a leaf, so obviously it's height balanced. So there seems to be some relationship between the left and right subtrees and this property of being height balanced. And so we can take a little bit more advantage of this property. And we can think, 1, let's check if the left subtree is balanced. So the idea here is checking if the left subtree is balanced. Consider this tree right here. Well, clearly this tree is not height balanced because we have this one path over here that's much longer than this path of 1. And even if we look at this left subtree, we see that it's also not height balanced because here we have a path of 1 and here we have a path of 3. However, if we know the right subtree is balanced and the left subtree is balanced, then all we need to do is look at their differing heights. So for example, this subtree right here is height balanced. However, the whole tree is not height balanced, and that's because the height of this tree is 2 and the height of this subtree over here is 0. And so this idea that 2 minus 0 gives you 2, which is greater than 1, informs us that this tree is not height balanced. So we'll check if the left subtree is balanced. We'll check if the right subtree is balanced. Because again, if the right subtree is not balanced, then we know immediately the whole tree cannot be balanced. And then finally, we'll check if the height, of the left subtree minus the height of the right subtree is less than or equal to 1. And this is going to be the absolute value. And the nice thing about the height function is when we start at the root and we go down to the left subtree, we can simply have height as an additional parameter, and we can add 1 to it every time we go a depth lower in the tree. We are able to compare the heights in constant time. So if these 3 conditions are met, then what you'll do is return true. otherwise you return false. And so the important thing here is step 1 and step 2 are actually recursive calls in and of themselves, because to check if the left subtree is balanced, you're going to call this method, and then that left subtree is going to call that method on its left subtree, and so on and so forth. And so what you'll return for all the sub functions is going to be 1, 2, and 3. And actually this is sufficient. We don't need this other statement here. We can simply return the value. Once we return this value, if any of these is false at any point in the tree, we'll always be returning false because one of them will be false. So actually we're going to want to return 1 and 2 and 3. Okay, great. So that's the idea for determining if it's height balanced. And there's actually some code right here that we use to do this. And so this main function is called throughout. So here we have LH and RH, which stands for left height and right height. So obviously we need some base case for our recursive call to prevent some stack overflow. And so we've established this height function. The height function can be folded into this method by adding an additional height parameter. And whenever you make these recursive calls down here, you could just say is balanced left, comma, left height plus 1. But let's just assume we have this height function. Then what we can do is make those 3 calls that we said above. So 1, we want to check that the left subtree is balanced, the right subtree is balanced, and the absolute value of the left height and the right height is less than or equal to 1. So that was condition 3 from the slide above. So if all of those things work, you can return true, otherwise you return false. Again, it's equivalent just to returning those 3 conditions since they are being ANDed together. Our next question asks us to determine if a tree is a valid binary search tree. And so for this question, we have to think about what a binary search tree is. And so there are 2 properties we need to evaluate. 1, that this tree is binary, and 2, that this tree is a binary search tree. Now it may be a bit difficult to validate this first property, the property that this tree is a valid binary tree. This would require us to iterate over each node in our tree and see that each node does not have more than 2 children. One other approach would be to look at the implementation of this tree. For example, if we have a node class that only has a left child and a right child, then we know this tree is a valid binary tree. However, if the node class stores children as lists, then we know we may not have a valid binary tree. Most times this question is phrased as, determine if a binary tree is a valid binary search tree. So there's no need to validate that this tree is a binary tree. I bring up this first point just as a reminder that it's always important not to make assumptions about the data structure you're working with, or place any additional restrictions on your tree. So let's assume we validated that this tree is a binary tree. The next thing we need to do is validate that this binary tree is a binary search tree. And so the one property that we need to verify is I'm going to say left descendants are less than or equal to a node, which is less than or equal to the right descendants. And for this, I'm just going to make this inequality strict. Okay, so thinking about the approaches to this problem, there are a couple ways we could take it. One would be obviously some sort of recursive approach. So let's just naively think that if we can validate that both the left and the right are binary search trees, the whole thing is. So this is kind of the recursive approach of 1, validate that the left subtree is a binary search tree. 2, validate that the right subtree is a valid binary search tree. And 3, validate that the left node is less than the current node and the current node is less than the right node. And if all 3 of those work, then we return true, as this is a valid binary search tree. Okay, so let's just check if this approach would work on some input. So here we can check that the left subtree is a binary search tree, and we see that 2 is less than or equal to 10, which is less than or equal to 30, which is great. That is a valid binary search tree. This right node actually is not a right subtree, so we wouldn't need to check it. So first one passes, second one passes. And our last check here is to determine if the left node is less than or equal to the current node, and the current node is less than or equal to the right node. So we see the left node has value 10, and since 10 is less than 20, and 20 is the value of the current node, the left side passes. We also see that 20 is less than or equal to 30, so the value of the current node is less than or equal to the value of the right node. So the third check passes as well. So it passes all 3, so this must be a valid binary search tree, right? But it's not, right? Because 30 is bigger than 20, and we know 30 is a left descendant. And we need some way to keep track of a lower bound and an upper bound. And I think a good way to illustrate this property is to think about three kind of weird trees. So let's think about this tree here that only has left descendants. Let's think about this tree here that only has right descendants. And let's think about this tree here that zigzags. So this is a left child, right child, left child, right child. This child here is a left subchild of the root. And so let's assign these values too, just to keep track of things. In red is going to be the bounds. So initially we know a has to be less than infinity and greater than negative infinity. And those are just kind of stand-in bounds because a can be anything. However, we know that b is a left subchild. So b has to be bigger than negative infinity still, but it also has to be less than a. Now c is a left subchild of b. So we know that c has to be bigger than negative infinity, but it also has to be less than b. Similarly, d needs to be less than c and just greater than negative infinity. And again, these negative infinity is just kind of a stand-in. So let's take a look at how these kind of slid. So when we go to the left, we see a goes to the right, b goes to the right, c goes to the right. And so this makes sense because when we go to the left, we know whatever node we were at previously is an upper bound now because all left descendants have to be less than this node. So now let's take a look at this tree here. Initially, a has to be between negative infinity and infinity. Well, now let's look at b. So we know b is a right child of a. So we know b has to be greater than a and simply less than infinity. Similarly, c has to be bigger than b and less than infinity. C has to be less than d, less than infinity. And again, when we move to the right, things shift left as the previous node becomes a lower bound. And the nice thing here is we know a has to be smaller than d, right? And so we get this property by the successive chaining. A is less than b is less than c. Well, that means a is less than c. A is less than c and c is less than d, so a is less than d. So these properties are satisfied, and we really only have to worry about the most previous node. So I'm going to shrink these two a little bit. Let's take a look at this last one. So as usual, a has to be less than infinity and bigger than negative infinity. However, when we go to b, we know that b has to be less than a because it's a left child. So we know b has to be less than a and b has to be greater than negative infinity. Now we go to the right, and so we know b has to be less than c, but c also has to be less than a. Now let's look at our last node, d. We know d has to be less than c, but d has to be bigger than b because it's a right child of b. And so let's look at this pattern again. A starts from negative infinity to infinity. We know b has to be less than a. So a moves to the upper bound. Next for c, we know c has to be bigger than b. So b moves to the lower bound. And we can think this is a left move, a right move, and c has to be less than a. So this value is maintained. And then finally for a left move again, we know d has to be bigger than b, so this value is maintained, and d has to be less than c, so the current value slides over. So there are sort of a few things to check. 1. Well, we got to check this condition right here. And so what we're going to do is start off by defining a function. So we're going to say valid BST, min, cur, and max. Now, when we recurse down the left subtree, the minimum value is going to stay the same, and the current value is going to become the maximum. So 1, check that min less than cur less than max. Next, we want to call it on the left subtree. So we're going to call valid BST. Min's going to stay the same. We're going to say cur.left.value. And I know current's kind of being used as an integer in a node here, but it's not anything structurally different. Then we'll say valid BST min, current.left.value, and then the max is going to now become cur. So we'll call that function and see what it returns. Similarly, if we move to the right, we're going to call valid BST, our min is now going to become our current node. Our new current node is going to be current.right.val, and our max is going to stay the same, so it'll just stay as max. And here that's written in a little bit cleaner in some code. If there is no root node, if the root node is defined as null or anything like that, then just return true. But otherwise, we're going to check these conditions. So 1, we're going to check that min and max are not null and that the equality holds. So we want to check that it's less than the min and greater than the max. And again, here we use weak inequality, but that's fine. I mean, we could change that very easily. And then what do? We return the left subtree, and again, our min value has stayed the same, and our max value has become our root, so our current node. When we recurse down the right subtree, the current value moves to the min, and the max is maintained. And if this explanation doesn't seem that intuitive to you, or if you're still hesitant about if it would work, I'd really encourage you to draw up a binary search tree, run this algorithm on it, and see what you come up with. At each step, you'll see how the min, max, and all the others update. The one last thing I would like to note about this problem is, let's say you blanked on this algorithm and you're having a lot of trouble. Well, we can actually leverage a property we learned about earlier, which is tree traversals. So think back to the tree traversals, right? We saw there were pre-order, post-order, and in-order. And they were all relatively easy to implement. It was mostly a base case and then 3 lines of code. Remember that left, right, and visit? And it's important to note that the in-order traversal has a property that on a binary search tree, it will be in sorted order. And the reason to think about that is the in-order traversal will first print out the leftmost node, then its parent, and then any right children of that parent. And so that property will guarantee that the smallest node, followed by the second smallest node, followed by the third smallest node, etc., will be printed out. So theoretically, if you were having trouble developing this algorithm, you could run an in-order traversal of the tree, store all the elements in a data structure, and then traverse through that data structure and make sure every element was greater than the element to its left and less than the element to its right. That would be most helpful, and once you validate that, you know you have a valid binary search tree. So never be afraid to approach problems in a little bit of a different fashion, especially if you're having trouble going through an algorithm you had experience with. The next problem we're going to look at is, given 2 nodes, determine the LCA. And again, if you're given this problem and you have no idea what the LCA is, you're going to want to ask a question about that. Also, you might want to ask a question about these 2 nodes. Are these 2 nodes in a graph? Are they in a tree? Are they in a binary search tree? Because this problem actually changes given what kind of structure the nodes are in. So LCA is the lowest common ancestor. And so for some tree, the lowest common ancestor for, say, this node and this node is this node here. C is the first node that both A and B have in common. Note that A and B also have the root node in common, but C is a lower node than the root node. And so for this problem, let's restrict it to say given 2 nodes in a tree. Because in a graph, we might not have a connected graph, in which case 2 nodes wouldn't necessarily have an ancestor. Also, in a graph, as we've discussed, the idea of parent-child relationships kind of breaks down, more so than it does in a tree. So let's assume we're given 2 nodes in a tree. Note that all nodes in a tree will have a common ancestor, and that's the root. Pick any 2 nodes, you know that they're going to meet at the root, since the root is the ancestor of all subnodes in the tree. So this question 2, let's think about this. How could the implementation of the tree affect this answer? And I think there are 2 key points we need to consider here: binary search tree and parent references. So again, I'd encourage you to pause the video and think about how these 2 could affect the answer, especially if you hadn't thought of these before. So let's think about the second one first, parent references. Most time in a tree, you are given, for any node, say node C, you are given the left child and the right child. However, let's say you were given parent references. Well, then our algorithm could change a lot, because we could leverage this in some way. And here are those 2 that I mentioned. So let's think about if we had parent-child references. And let's say I took 2 nodes that were seemingly pretty far apart, so those 2. Well, once I'm given this node, I know that I can work my way back up the graph. So I could find that parent, and that parent. So I could work through this graph and figure out that those are my ancestors. Then let's just say I stored this in a hash set. And I stored these as A, B, C, and D. So I know B, C, and D are in my hash set. Well, then what I could do is begin at this node over here, we'll call it E, and I could do the same thing, where I work up this tree. Start here, and check if it's in my hash map. If it's not, then I continue. Is this in my hash set? No, it's not. Is this in my hash set? No, it's not. When I get to D, D will be in my hash set, so I'll know that there's a collision. So if I'm given parent references, then I could do this in pretty quick time because I would only have to traverse log n nodes, and for each of those nodes I could do it in constant time, checking if it's in the hash set or adding it to the hash set. This would require log n memory because we're going to have to store log n nodes, but again, that is not too crazy of a memory constraint. However, we might even be able to do a little bit better with a binary search tree. And so, as we said in the lecture, if you're ever given a binary search tree in an interview, you always should look to leverage the binary search tree property in some way. And so let's think of an arbitrary graph again. And so let's say I'm given these two nodes here, I and G. Well, we know the values of I and G because we're given I and G to start the problem. So let's say we take two values, let's say ival equaling I.value and gval equaling G.value. And we start at A. Well, we can look and compare these values to A. And the underlying idea is if ival and gval are both bigger than A, then we know these two nodes are in the right subtree of A. And that follows from the binary search tree ordering property, because we know any nodes with value bigger than that occur to the right. So let's just say we check and we see ival, gval are greater than A.value. Well, then we know I and G have to exist somewhere over here. Now we do the same thing for E. We look at E.value. Well, we see gval is bigger than eval, which is true because G is a right descendant of E. But we see ival is less than E.value because I is a left descendant of E. And so we know at this point they've split. I is in one subtree and G is in another subtree. And this is the lowest point at which they would split. So we can say that E must be our LCA. And so the implementation in code is pretty straightforward, and I'd encourage you to work that out on your own. But this is the great property of binary search trees, in that we know as soon as one of the nodes' value is less than some node and the other node's value is greater than this same node, we know that they can't exist in the same subtree. So that's their lowest common ancestor. So if we go back to the original question, all we were given was given two nodes, determine the LCA. And so this is a great example of how restrictions on what type of tree it is, details on the implementation can change the question a lot and make it really quick. Because in this implementation, we had some additional memory requirements. Here, we don't have any of those memory requirements, and it's still going to be solved in log n time, where n is the number of nodes. So we were able to improve our solution even further by taking advantage of a property of the tree. So this is a question that underscores the importance of questions. The last exercise we're going to look at is a debugging exercise. So the problem reads, given a graph, the algorithm is supposed to determine if there is a connection between node A and node B, and the node class is given below. Since this is a debugging exercise, we know some bug exists in the code on this page. So we see we have a bunch of code here, and we have this method connection exists that sees if there's a path between node A and node B. But before we dive into that, it's important to review the node class above. So we have this node class here, and it seems to have two member variables, some integer representing the data it holds, and an array list of nodes that is called children. And as mentioned before, it may not be best to think about graphs as having strict parent-child relationships, so we could just also think of this as all the adjacent nodes. So let's take a quick glance at this code here and try to get an understanding of what it does. So right off the bat, we know it returns a Boolean variable, so true or false. The method name also gives us a little bit of a hint: connection exists, which comes from the problem statement as well. We see it takes two input parameters, node A and node B. So node A and node B are the nodes we're starting with, and we are trying to determine if there is a path between node A and node B. So let's take a look at the actual code. We see this code instantiates a hash set to keep track of the nodes we've already visited, and it instantiates a stack of nodes. We see it pushes an element onto the node stack, and then iterates while the node stack is not empty. So given the structure of a stack and this while loop, we can reasonably assume this is an implementation of depth-first search. And we know depth-first search is an exhaustive search, so if there is a path between node A and node B, depth-first search will find it. So let's look at this while loop. While the node stack is not empty, we pop an element from the stack right here. Then we iterate over all the children of this node. And like we just mentioned, these are all the adjacent nodes to this node. We see if the child equals B, and we return true. Now one thing we can check right off the bat is, what's the type of child? Well, child is a node. And what's the type of B? Well, B is a node. So this works well. We are comparing elements correctly. The next thing we do is we push on the child to the node stack, and we add the child to the set of visited nodes. Once the while loop terminates, we return false. So another thing we could check pretty quickly is the return type. We know it's a Boolean, and we see in our code that the only values returned are Boolean values. And we know that a Boolean value will be returned before our method terminates. So return type looks good as well. And so after looking through these elements of the code, if you're still not able to identify the bug, it might be a good time to run through an example. So let's just say we have some graph. And when creating examples, it's helpful to think back to the types of graphs. So graphs can be acyclic or cyclic. So let's add a cycle in here. Graphs can be directed or undirected, but luckily here the direction of edges should not play too big a role. And then finally, graphs can be connected or they can be disconnected. So why don't we make our graph disconnected? And let's see what works. So first, let's say A and B are in the same connected component. So let's say I have A and B here. Well, clearly a path exists from A to B. There are actually multiple paths from A to B. So our algorithm should return true. We'll keep track of the elements in our stack over here on the right. So first, we push A onto our stack. So A is on our stack. We then pop A from our stack, and we add those nodes that are adjacent to A. So let's call these nodes X and Y. So let's say we add X to our stack, and then we add Y to our stack. Well, our next thing will be to visit Y. On our next iteration, we'll visit X. So let's say we've already visited node A, and we're at node X. So both of these will be added to our set of visited nodes. Well, when we get to node X, we've removed it from the stack, and what we'll do is then push on those nodes that are adjacent to X. And so the nodes that are adjacent to X are A and Y. And you see the problem. We are going to go back and search A, although we've already visited A. And the problem here is that we have successfully added nodes to our visited nodes set, but we never check if we are accessing a node that is already in our visited node set. So this is going to cause the bug that we revisit nodes. What we'll need to do is add a piece of code in here that actually checks to make sure that we haven't seen this node already. And this is a simple one-line if statement. And it says, if the child we're looking at is not already in our set of visited nodes, meaning that we haven't visited this child yet, then let's add it to our stack, and let's appropriately add it to our set of visited nodes as well. This will ensure we never visit nodes twice, and it will make sure our depth-first search doesn't get caught in a loop, as it did in the example above. And so just a note about debugging, you don't necessarily have to remember the algorithm perfectly and then compare and contrast it with the code you have, because you might get a piece of code that's not an algorithm you know or you've seen before. In that case, it's really good to think about various elements of the code. So for example, does it return the correct type? Does it use the correct data structures throughout? Then working through an example can be helpful. And it's important not to cherry pick a nice or an easy example. In the above, that could be an acyclic connected graph. You would want to test on sort of nastier inputs, disconnected graphs, or cyclic graphs, as that might help stress test your code. So the last part about debugging problems is that it's always best to have as much information about the bug as possible. For example, if the code's not compiling, you might have a problem with your syntax. If you're getting a Stack Overflow error, then it might be an error with your recursion. And even if the code is running and compiling correctly, understanding the behavior can be helpful. So for example, if we were to run this code on a graph that has a cycle, it would run forever as it would continually check nodes it's already seen. So if you have code that's running forever or taking way longer than it should, you might think to yourself that you have a bad guard on your while loop, or that you might be duplicating work. In all of these instances, understanding the bug, understanding the current behavior, and understanding any errors can really help you to solve this problem, and can help you debug your solution into one that works. And so this concludes the exercises for trees and graphs. We'll make sure to include some additional exercises if you'd like some more practice, and we'll make sure to link those in the description below. We hope you enjoyed this video, we hope you found it beneficial. If you're still struggling with any concepts, know that that's totally normal, and that sometimes this takes a little bit of time and practice to get. So feel free to look at the lecture again, feel free to look at these examples again. Lastly, if there's anything confusing about this lecture, feel free to leave it in the comments section below and we'll clear it up. Also, if you'd like to see any specific topics or specific questions covered, feel free to fill out that form in the description below, and hopefully we'll get to your topic soon. Thank you for watching. We hope you enjoyed.